Good morning. This is just a quick walkthrough of the geometric distribution notes for my quarantined students. All right, so on our last video, we talked about the binomial distribution. It had a couple of key features. Remember that a binomial distribution is a very special kind of probability distribution in which there are only two outcomes, success and failure. Success is the thing we're counting, failure is the thing we're not interested in. The probability of success is the same on each independent trial. And we have a fixed number of outcomes. So we're talking about x out of n. In this case, for geometric, these are sometimes called waiting time distributions. And what we're really interested in is not how many successes out of a certain number of trials, but how long do we have to wait until we get a success? So it's got a lot of similar features. The first feature that's similar to the binomial distribution is that there are still only two outcomes, success or failure. So at the beginning of the problem, you know what you're counting. I'm looking for red or not red. I'm looking for even or not even. The probability of success is still a lowercase p. The probability of failure is still that complement, 1 minus p. And the trials are still independent. So it's important that each time you do a trial, like each time I roll a die or pull a card or open up a cereal box, I know there's the same probability of success in that situation. The difference is that x is no longer going to be a discrete random variable that's counting the number of successes. Instead, x represents the number of the first success. So if I flip a coin and don't get even until the 7th time, then x is 7. All right, every time you do this, every single time you do a geometric problem, if you're going to use the probability of a geometric distribution or you're going to use the mean or standard deviation, you are going to write down this is a geometric distribution where p equals and fill in the blank with that probability. Notice you don't have n because for a geometric distribution, you don't know how long you're going to do it. You may have to do that many, many, many times. All right, so when you're going to find geometric probabilities, we've already done this, we just didn't have this name on there. So for example, if I roll a die until, now as soon as I see that until, I know that I'm talking about geometric. So I underline that, woo, geometric, there's no fixed end value. I'm going to do this until I get a success. Until I get an even number, what's the probability that my first even occurs on my fourth roll? All right, so I would ask myself, what's success? I'm counting evens. All right, so success is the even. So we're doing this until we get an even number. And we want to know what's the probability that our first even is on the fourth roll. Okay, so for a geometric distribution, okay, this is geometric, it's waiting time. I know the probability of even is 0.5. I can do this without a calculator. If I know it's got to be until I get an even. So the fourth roll is going to look like odd, 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 even. So 0.5 for odd, 0.5 for odd, 0.5 for odd, 0.5 for even. I can also do this in my TI-Nspire. Let me bring this up really quick. Okay, so in my TI-Nspire, I'm just in a scratch pad. I'm going to go Menu, Statistics, Distributions, and I have to scroll way down, and I want the one that says Geometric PDF. This is for a single probability. Okay, or sorry, a single value of x. So the probability of success was 0.5, and I want my first even to be on the fourth roll. So x is 4. There, I hit OK, and I get that 0.0625. All right. The next one says, historically, about 60% of the people in your community wear green on St. Patrick's Day. Find the probability that you see someone wearing green before the third person you encounter. Now, there's a couple of options here. First off, it's waiting time because could it be the first person wearing green or the second person wearing green? So there's two options. So we're going to have to calculate more than one probability here. All right, so I know that success was wearing green because that's what we're looking for. And so this is going to be geometric. And the probability of success, according to our problem, is 0.6. Feels like this should be independent if we're talking about random selection. I'm a little concerned when it's talking about you see someone wearing green before the third person you encounter, that there may be some lack of independence there. If you happen to walk through a parade on St. Patrick's Day, these probably wouldn't be independent. So let's just assume independence here. So if I was going to do this by hand, the probability I get green before the third person could be the first person wearing green, or the second person wearing green. That would look like not green, green. All right, so the first person wearing green, that would be 0.6. Okay, the second person would be 0.4 for the one that's not, times 0.6 for the one that is, that's 0.24, and that gives me that 0.84. Okay, I could also do this in my TI-Nspire. Let me bring that up really quick. Okay, this because I'm doing multiple probabilities here. I'm going to go Menu, Statistics, Distributions, and I'm going to scroll down and find, where did it go? There it is. Oh, I saw it and then I lost it. Geometric CDF. This is for a range for more than one X value. So the probability of success for wearing green was 60%. The lower bound was 1, and the upper bound in this case was 2, because I was interested in something happening before the third. Before the third. So not including the third. All right. So I'm going to hit OK, and there's my 0.84. All right. When we're talking about the mean and standard deviation, these formulas are on your formula sheet. And notice it says if X has a distribution with if X has a geometric distribution with parameter P, then the probability that X equals X is 1 minus P to the X minus 1 times P, where X is 1, 2, 3. Now think about this. All this is saying, I'm going to scroll back up here. Okay. For example, one of my first roll is, the fourth being even. So that would be 3 odds followed by an even. Okay, so here's that 1 minus 0.5 to the 4 minus 1, 3 odds times the 1 even. Or when the second one was green, okay, the second one being green, that would be X equal 2. I would have 1 minus P, that's 1 failure, 0.4, okay, to the 2 minus 1, 1, times that probability of success. So if you're going to do this by hand, you don't really need this formula because it's very logical of how this is calculated. Now, one thing you don't want to have to memorize, though, is the mean and standard deviation. So to find the mean of a geometric distribution, you take 1 over P. This will give you the expected value of the first success. And then the standard deviation is the square root of 1 minus P over P. Now, in our problem, if X is the number of the first person you see wearing green, the mean of X would be 1 over P, or 1 over 0.6, which is 1.667, okay? And the standard deviation comes up to about 1.05. So you see, I just substituted the 0.6 into the formula and solved for those. Now, in this case, these are kind of weird to interpret in this context. So another way to think about this is we expect that the first person wearing green is the 1.6th person in this situation. So we expect to see either the first or second person going to be the first person we see wearing green. And that typically 1.05 is, about 1 is the difference between the first person we see wearing green and what we actually observe. Okay. All right. So again, with our TI-Nspire, we can do a lot of this, and you can do a lot of these by hand as well, and they're very easy to do. So with the TI-Nspire, for example, 43% of students who drive to school carry jumper cables. So the situation is we want a single value of X. So when we're talking about a single value of X, we're going to go for the one that says geometric PDF, or probability density function. This gives us 1 X value. Okay, so suppose you stop cars until you find a student carrying jumper cables. As soon as I see that word until, I think, aha, geometric. And what am I looking for? I'm looking for jumper cables. So success would be jumper cables. What is the probability that you have to stop 5 cars? Okay, now what that means is that the first person with jumper cables must be that 5th car. So it was like no cables, no cables, no cables, no cables, cables. Okay, so this is geometric because it's waiting time. According to this problem prompt, 43% carry jumper cables. So there's my 43% is the probability of success. And X in this case, again, represents the number of the first car with cables. So if I have to stop 5 cars, that means that 5th car must have been the one carrying cables. So you could do this just by hand. That means no cables, no cables, no cables, no cables, cables. All right, so that would be 0.57. That's the no cables, failures, to the 4th power times the 0.43 for cables. That gives me 0.045. The other thing I can do is bring up my TI-Nspire here. And I'm going to go, because this is a single value, I'm going to Menu, Statistics, Distributions. And I'm going to scroll down and find the geometric PDF. Okay, probability of success was 0.43. And the first success I wanted to be this, the 5th car. Hit enter. And there's that 0.045. Okay? All right. Now, if you want a range of X values, you're going to use that geometric CDF. Remember that stands for cumulative. So we're putting several together. So suppose you want to stop random cars until you find a car carrying jumper cables. What is the probability you will find a car with jumper cables before the fourth car? It means you don't have to stop the fourth car. So that must be the first car or the second car or the third car must have had jumper cables. Okay, so if I wanted to do this by hand, I would say, okay, it's geometric. P is 0.43. It could be the first car, that's 0.43, or the second car, that would be failure, success, 0.57 times 0.43, or the third car, failure, failure, success, 0.57, 0.57, 0.43. I take all of these, I add up these three products, and I end up with 0.815. Or we could use our cumulative function. In this case, we're going to think it could be the first car, that's the lowest number of x, or it could be the third car, that's our highest value of x, because it says before the fourth car, before the fourth car. All right, so I'm going to go to my handy dandy calculator here. Here we go. So menu, statistics, distributions, and I'm going to go find geometric. Oops, did the wrong one. Let me try again. Menu, statistics, distributions, and I'm looking for geometric CDF. There it is. All right, so probability of success was 0.43. The lower bound was 1. Isn't it nice that it defaults to 1 to remind you that the first one would have to be 1? All right, and then the upper bound would be 3. And there's that 0.815. Okay. All right. Now, suppose you completely forgot to study for your pottery styles of the ancient world quiz. Oh no. And you have no idea what the answers are. And you have to guess on each question. The quiz consists of a photo with 5 different choices for the pottery style. And says, let X equal the number of the first question correctly guessed. It says, what's the probability you get the first question correct? All right. So if we're talking about the first question correct, we're talking about a geometric situation. We know that if there's 5 choices, correctly guessing would be 1 out of 5 or 20%. So the first question, 20%. Okay, no math, no formula needed for that. What's the probability that your first correct guess was the third question? Okay, so you could do this by hand and you could say failure, I got it wrong, failure, I got it wrong. My first correct guess is the third one. Wrong, wrong, right. 0.128, or you could use the geometric PDF menu, statistics, distributions, geometric PDF. Probability of success is 20%, and we're talking about the third question being the first one correct, 0.128. All right. What is the probability you get a correct guess before the fifth question? Before the fifth question. All right, so this will be geometric, 20% chance of success. Before the fifth means not including the fifth. It happens before then. Okay, so that's kind of different than like on the third. Okay, so before the fifth means I'm going to have like 1 or 2 or 3 or 4. It could be the first one or the second one or the third one or the fourth one, but it happens before the fifth question. So that's going to be a lower bound 1 or an upper bound 4. I think this one's faster to do in the calculator. So menu, probability, distributions. I'm going to find that geometric CDF. Probability of success, 0.2, lower bound 1, upper bound 4, and there's that 0.5904. What is the probability it takes you more than 4 attempts to get a correct answer? Now, on this one, I happen to notice that we had just already done this problem, okay, and more than 4 would be 5, 6, 7, all the way up to infinity. So that's the complement of what we just did. So the easiest way to do this would be to actually just take the complement. It's everything else, okay? If it's before the fifth, that's 1, 2, 3, 4. If it's more than 4, okay, then it would be, and I say greater than or equal to, yeah, greater than or equal to 5. More than 4 would be 5, 6, 7, 8, 9, 10. That's the complement. So 1 minus there. Now, if you want to do this in your calculator, think about what this would mean in lower bound and upper bound. All right, so your lower bound would be 5 because that's more than 4, the first number that's more than 4. And your upper bound would be infinity. So if I want to do this in my calculator, geometric, okay, menu, statistics, distributions, I'm going to go find that geometric CDF. My probability of success was 0.2. My lower bound is going to be 5. And my upper bound is going to be infinity. Now, for me, I'm usually too lazy to go hunt up the infinity button on this, so I'm just going to type in 10 to the 99th power right here. That's going to give me something that's really, 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 really big and essentially good enough for infinity in this case. If you're looking for the infinity button, I believe if you press, is it this little... Nope, that's the wrong one. See, this is why I don't use it. Pi button, there it is. In the pi button, maybe? Nope, still not in there. Maybe I don't know where it is. See, this is why I shouldn't do these kind of things on a video. What are we going to do? All right, but we're not going to use the pi button anyway. If you find that, okay, 10 to the 99th, and I will go looking for that infinity button. All right, so I'm going to click OK, and I get 0.4096. Notice that's the same answer I got by just using the complement. Okay, so on which trial do you expect to get your first success? So remember, expected value is mean. Expected value is mean. So I see that word expect. I'm going to do the mean of x is 1 over p. I'm getting that. I'm still geometric. So that's 1 over 0.2. That would be 5. I expect to get my first on the 5th trial. Okay. All right. Last question. Okay. I think it's the last question. Oh, nope, more than this. Among the administration staff in your company, 25% have never been married. Okay. This is a weird question I made up and then it didn't work out very well. So just bear with me. You are planning to conduct an interview with 20 administration staff members about satisfaction with health benefits. Now, when I look at this to begin with, this feels binomial to me because N is 20. Okay, so it's a fixed number of trials. And then it says that we're talking about never married. Okay, so 25% have never been married. It says, what's the probability that if you select admin staff at random, you will not interview a married person until the 10th interview? So this is kind of like a bait and switch here because it starts off, it feels like it's binomial because of these 20 administration staff. So you're planning to conduct this, but it says you won't interview a married employee until the 10th interview. So until the 10th tells me that we're talking about geometric because it's waiting time. I'm looking for a married employee, and so 25% have never been married, so we're going to assume that means 75% have been married at some point in time, okay? All right, so the probability of sex is 0.75, and that gives me 10 here for our trial. Okay, so X is the number of the first married employee. See how I defined that variable? You need to define your variables if you're going to use them, okay? Because you can't just say X is this and X is that and X is this because it's going to change throughout the course of this problem, okay? So the probability that X is 10, the first married employee is the 10th one. You could say, well, that's 25 non-married employees followed by the one married. Okay, using the formula, you get 0, or you could do geometric PDF. When you do that, you're going to enter in 0.75 and 10. Either way, you end up with 3 to the negative 6, which to 4 decimal places, 5 decimal places even, that is basically 0. Okay, now it says if you interview at 20 admin staff members, okay, so there's that fixed number of trials again, what's the probability that exactly 5 have never been married? Okay, so in this case, we're going to a binomial distribution because in this one, there is a fixed number of trials, okay? N is 20. The probability of success, in this case, we're counting X is the number of never married employees. So we've switched what the probability of success is. We've switched what X is representing. So we're talking about N equals 20. P equals 0.25 for married, and X is equal to 5. Now you could use the formula, combination of 20, choose 5, probability of success to the 5th, probability of failure to the 15th, and get this answer. Or you could use the binomial PDF. Okay, so remember that would be menu, statistics, distributions. Oh, scroll past it, binomial PDF. We're talking about 20 trials. Probability of success was 25%, and we want to know 5. Okay, and there's that 0.2023. Okay. All right, next question. A basketball player makes 80% of her free throws. We put her on the free throw line and ask her to shoot free throws until she misses one. All right, so the probability of getting a hit is 80%. It says, does this fit the geometric model for this situation? If so, what constitutes a success? All right, so the first thing for geometric is that it's waiting time. Are we waiting until something happens? Okay, so that seems pretty set. We're doing until she misses one. So what that means is that there are 2 outcomes, but the thing we're waiting on is a miss. So success is a miss in this case. And remember, the success is the thing you're counting. So even if in English it has a negative connotation to it and it's not a very positive thing, it can still be a success. It would mean failure would be a hit. So we've got that binary option. We're doing until, so there's no fixed number of trials. And then we have this thing about independence. Are these independent trials, is the probability that she misses the same each time? Okay. We're going to have to assume that for this to be geometric. So think about it. If she gets like a hot streak or a cold streak, because this is a sports thing, it's not like rolling a die, this would be a bad assumption to make. So if you know that this player is prone to, when she hits a shot, she's more likely to hit the next one because she kind of gets into a groove, or same thing, if she misses a shot, then it kind of messes with her head and she doesn't do as well on the second one. If that's that kind of player, which is probably true, this is probably a bad assumption. So we have to assume that this is independence in order for this to be geometric. And that might be a little bit of a stretch. Okay. For this case, X would be the number of the first successful trial, which means the first missed shot. And the probability of that would be 20%, not 80%. Okay, a teacher pulls cards out of a standard deck of 52 cards without replacement and notes if the card is red or black. If she pulls out 10 cards without replacement, what's the probability that exactly 4 cards will be red? Does a geometric, binomial, or neither fit this situation, and explain? All right, so in this case, what we would be looking for, okay, first off, is there success and failure? All right, so we're looking for red. Okay, so red and not red, that feels binary. All right, is there a fixed number of trials? Yes, 10. Now, fixed number of trials feels binomial instead of waiting time, geometric. So right now we're at the binomial. If it's binomial, we need to know the probability of success. That would be red. Probability would be 50%. And then, are those independent? No. All right, this can't be geometric or binomial because it says in the problem without replacement. That means that those trials are not independent. Or in other words, the probability of red isn't fixed. It's not going to be the same each time. The first time it's 50%, the second time it's going to be 49-ish, the third time 48, etc. So this is not independent, which means this doesn't fit either of our circumstances. So we would not be able to use our binomial or geometric formulas to make this happen. All right, if you have any questions, please let me know.